Hi, this is Group 10 and this is a summary of what we did for Task 1. Our problem statement. Our group aims to use multiple linear regression to predict daily new deaths at a particular point in time in the European region using Python and Excel. We then compare the Python model results with that of Excel before evaluating the reasons for the differences. For preparing the dataset, we decided to use the European region as the countries in the same region are likely to experience similar trends due to comparable conditions. Cleaning up of data. Due to discrepancies in the dates and countries of data given, such as missing data for certain countries or different dates recorded, we first removed all the countries that had missing data and then analyzed the data to choose the dates that were representative of the remaining countries. After our first iteration, we dropped countries entirely which did not have values for certain date ranges. Initially, we chose the start and end date for our data to be 24th March 2020 to 4th May 2021, as majority of the countries in our dataset contain values from these dates. However, because of COVID-19, which was only beginning to start spreading during that time, the number of cases per day was relatively low as compared to the later months, causing a lot of outliers in the scatter plot of the data. Hence, we decided to choose a later date to run the regression model. After additional adjustments to the date, our group finalized on the date range of 1st May 2020 to 28th February 2021. We also dropped countries which we found to be outliers depending on our first plots. Next, we used the pandas library to spot outliers that had disproportionately large values within the dataset. We used the group by function in which we grouped the data according to the country and then sorted the values in ascending order so that we could find the maximum and minimum. Over here, we can see that the UK had 2 million active cases, whereas Iceland had 1,252 active cases, which are disproportionately large and low respectively, and thus were deemed to be outliers. We use this filter function to remove these outliers. Our final data set, after removing all the outliers and deciding on the date range, consisted of 24 countries. Here is our final data set. Now Danny will talk about the iterations of our multiple regression model and our final solution.
For all of our models, the code for the linear regression is at the bottom of the Jupyter notebook. It is similar to the core implementation with the addition of the function for the adjusted R2 scores and the RMSE. In the first iteration of our model, you can see that from the graph, the pattern that appears is not very nice. Additionally, we have a very high mean square error. As such, we decided to try a different set of variables and ran the models with different features. The errors became better, but the graph and the errors were still not ideal. Hence, we tried a third time with other variables and ran the regression model again. This time, the results were significantly better than the previous one, but upon further analysis of the data, we found and removed outliers and discovered that some of the variables had a linear relationship with the square root of the new daily deaths. This is the linear regression code. As you can see from our results, the final iteration does seem to have much lower errors and a decent adjusted R2 score. We plotted the predicted and actual data to see how well the model worked. Some limitations of this model would be that it would not be able to predict unrealistically high values, and there might be minor inaccuracies in predicting small values. Additionally, we could try and use a multiple polynomial regression to see if the data fits better than multiple linear regression.
For task 2, our problem statement is we want to predict the positive ratio of COVID-19 cases in the United States. Why do we choose this positive ratio? It's because we can obtain the information of how much testing is being done and to understand the spread of virus. After we obtain the data set from Kaggle, we filter out the invalid values and we plot a graph for the positive, negative, recovered death to the ratio, the positive ratio, which is our target. We then remove the outliers, which is the ratios that are greater than 2. This is what we get for the MSE, our J score, and the graph of the total test results versus the positive ratio. We then try with other variables against the positive ratios. From the previous graph, we can see that the data is very scattered. Hence, we try to visualize them by grouping them into different states. We then categorize them into 3 categories, which is the first group, less than 100k, the second group, between 100k and 400k, and the last group, more than 400k. These are the respective graphs.
It is clear that more work needs to be done. Therefore, we decided to increase the number of categories that we initially had and to find a different way to separate the different states. In this case, try to separate in terms of their standard deviation instead, as it may give us more information about how the data is being distributed across the different states. Here are some of our results for the different groups with different standard deviations. As you can see, these different states still have vastly different trends from one another, and the results we obtained are not ideal. Therefore, we decided to look at other variables that we did not use previously in our prediction model. For once, we decided to see whether they are time dependent. Thus, we plotted graphs to observe the trend of positive ratio over time, and we tried to identify similar trends among them. As you can see in our graphs over here, some of the trends in positive ratio does seem to follow a trend according to time, and therefore we decided to proceed on and try to categorize some of these states. As you can see in this graph, these two states seem to follow one trend that looks like polynomial in nature, while the other three follow another that also looks like polynomial in nature, and therefore we decided to use polynomial regression as our machine learning model to predict the positive ratio of the states in the United States. We also decided to use another metric other than mean square error, called the adjusted R-square score, which can be used to predict accurately R-square scores for polynomials. In some of our results, we do have promising results. As you can see here, there's a low MSE and a pretty high R-square score. Finally, we decided to combine the states with good R-square score and to see whether we can create a robust prediction model that can predict multiple states in the United States. In our final results obtained, we managed to combine 4 different states from different groups, and using the polynomial regression model, we achieved a mean square error of 0.003 and an adjusted R-square polynomial score of 0.66. Although such a low MSE may seem ideal, this may be due to overfitting of our model. This arises because of the fact that we only use 4 states and across a specific time period. Therefore, using data from other states or other time periods may result in a very low accuracy of our model. In the future, we would like to try multiple polynomial regression on the datasets to predict positive ratio, and also try to identify certain similarities between these 4 states that resulted in having similar positive ratio trends, and therefore look at more variables which offer us further insight to why these states have similar trends. Thank you.